Good morning, everyone. So, everyone's fine today. Yeah. So we are on now the fourth day of the GAN course on chain of things, and today we will talk. We'll continue from where we stopped yesterday. Scalability in blockchains. So briefly, this is what we have seen before. Why scalability is important, and then we also looked into some scaling solutions. So we talked about payment channel networks, and we also discussed about side chains, and then we started looking at how data is being stored, and Ethereum data structures. Then okay, so we'll just go back here. We were asking this question: uh, can I um, So we were asking this question: can I improve the performance? Uh, when I talk about performance, it's like transactions per second in these blockchains, and can we improve the amount of data that's stored on chain? So both. So payment channel is the way. So we also said that you could improve the scalability by designing new consensus algorithms, but we also said that we could also do layer two scaling, which means that we do the computation off chain, and then we commit on chain. So for payment channels, we saw that even if you have many transactions, you could have only two on-chain transactions, and the rest could be off-chain. And you are opening and closing a channel, and we will see today another type of scaling solution, which we call rollups. So this is something that we have already seen. And we also talked about the state transition. Say, for example, the state SI, which is represented using a Merkle-Patricia trie, has a state root, which is written in the blockchain header. And after a set of transactions is executed in a block, so the state changes to something, say, as I plus 1. So essentially, a block contains a few transactions, quite a few transactions. And for every state, you have this storage structure. In this case, I've simplified it using a Merkle tree, but it is a Merkle-Patricia trie for Ethereum. Okay, so this is something that you have seen before. So we have seen that commitments, for example, help to send a message in a secretly, but and commit to a message and then open it later. So if Alice and Bob are sending, Alice and Bob are interacting, Alice can put the message in an envelope, seal it, send it to Bob. Because once it is in the envelope, you have to break the envelope to find it, and then that means that you have tampered it already. So this sort of commitment schemes have two properties: hiding and binding. The commitment reveals nothing about M, and binding property means that this the message is bound with this commitment. Alice cannot change her mind. Okay, so we'll talk about something else, which is called the vector commitment, because these are also very nice structures. So what happens in vector commitments is that instead of one element, you committing to one element, you commit to a set of elements. So think of a vector. Do you all know what is a vector? So think of it as an array, for example. You will see that v1, v2, v3 to vn. So it's a vector of length n, and you would commit to this vector. And when I say commit, it's like having this commitment gives a very short representation of the vector. So one property all these vector commitment schemes should have is a succinctness of the commitment. When I say succinct means short. you can, you have a very, irrespective of the length of the vector, the size of the commitment is very short. Okay, and it's independent. It's constant size, irrespective of the size of the size of the vector. It's a constant size commitment, and it's a short commitment. What we want to ensure is that when you commit to the vector, you send a small commitment to Bob. And what it means that this commitment will ensure that you cannot change anything in the vector. Okay, just like you cannot change an element or the message inside the envelope, here you cannot change any message in the any element in the vector. So first you will commit to the whole vector, and later if you want to open a position, so you can say you will give a proof of correctness. So you will call an open function where you will say give a proof that vi is an ith entry in the vector. So this is a proof that you will give. Now when I say it's a proof, you can think of a proof as a string. And we are going to talk about this in a bit. It's very hard to realize it at this point, so I will talk more about it. But what you want to do in the next step is that in the open step, you have to prove that vi is the ith entry in the vector. So at this point, just understand that you have a very short representation of the entire vector, which is the commitment. And the commitment will ensure that all elements are intact. When you ask for this position vi, you have to give a proof saying that vi is the correct entry, ith entry in the vector. Okay, so this is what you have to prove. And the Bob will be able to verify, will take the commitment, the ith element, the vector element at vi and pi, and it will say yes or a no if it's a verification is yes, if vi, the pi is a correct proof that vi is the ith entry. So essentially, the main idea is that instead of committing to each and every element in the vector, because you could have done that as well. For this one, first element, you are committing, you're constructing a commitment C1. Second element, you are committing to C2 and so on. You could have done that as well. However, and then think of each of these messages, each of these letters. You are committing, you are putting it in envelopes 1, 2, 3, 4 up to n. But instead of that, the beauty of this is that instead of committing to each and every element, you can give a short commitment and later be able to prove selectively which entry you want to prove. Look, let's look at an example to see how this works. Okay, I'll come to that later. But maybe before that, I'll tell you how it is used in an Ethereum implementation called a Verkle tree. So Verkle tree is a proposal that came from the Ethereum community, and Verkle trees were essentially used to reduce the length of proofs in Merkle trees. So if you have n leaves, what would be the length of a proof in Merkle tree? Log n. Yeah, log n. So you are giving the path somehow, not the exact path. We're giving some elements at each level. So instead of that, in this case, what you do is that your data is still in the lower layers, or not lower layers, I would say leaves. But instead of hashing it to this value, you will have a commitment, vector commitment for these values. So F0, F1, and F2, if these are the elements in the leaves, the commitment to these elements would be in the next level. Similarly, you can think of this as a vector. As I said, this is a vector. So this is a short vector. This is a element 3. The vector size is of length 3. So you give a succinct proof C1 from these, then a succinct proof from these C2 and C3, and then you take all these and generate a very short proof. Now these become your elements in the vector, and you generate the commitment of this. Why am I doing this? First question, why am I doing this? So the proofs are such that these are the proofs are independent. The proof size in this case is independent of the vector size. So the vector commitment that you use here would be such that the proof size is independent of the vector size, meaning that that in this case your height would be much less than a Merkle tree height. So main idea why Merkle trees were proposed is to reduce the proof size, because often if you have many accounts, you are not giving just account of correctness of one account, but you will be giving, say, correctness of multiple accounts, because when a transition takes place, multiple blocks are updated, multiple accounts are updated, right? So when the state changes from S1 to Si plus 1, many accounts are updated, right? It can be 100, it can be 1,000, it can be 2,000, for example. So if for every account, if I have to give a proof of correctness, then it's going to be log n into the number of accounts which have been updated. But instead, if your log n or the height is reduced, then it will be much smaller. And then there are also interesting properties that can come about with Merkle trees that can reduce the size of the proof. So at this point, even if you don't understand what is the relation with vector commitment, so on and so forth, these are really not easy to see, quite intuitive to see. But what I want you to take back is that there are alternative ways of storing data. And Ethereum, for example, has this proposal of Merkle trees, where the proof size is supposed to be much lower than the current design. Yes.
Define what is pi I.
Pi I is a proof. Pi I is a proof of correctness. That's the correctness of I.
So that on the leaves there are proofs of each element in the vector, and then we are combining those proofs to form a commit. So
no, not the commit. No, okay. So this one will be separate. I've written it just for representation purpose. So you are committing to F0, F1, and F2. Okay, and the pi 1, pi 0, pi 1, and pi 2. So the C1 is equal to F0, F1, and F2. And the pi 1 says, pi 0 says that F0 is a correct element, F1 is a correct element, and F2 is a correct element. Okay, any more questions? Okay, so even if this is essentially a bit hard to understand, only thing that you take from this slide is that apart from Merkle-Patricia tribe, there are other ways of representing Ethereum data. Okay, so transaction data. Sorry, just account data. Yeah.
So both Merkle tree and Merkle tree are used for Ethereum.
Yeah. Merkle-Patricia tribe.
Okay.
And
so what's the main difference between those two trees?
Yeah, that's what I said. The proof size is short.
And is this a proposed replacement of the Merkle-Patricia tribe?
It's a proposed replacement of the Merkle-Patricia. Okay, so so many people, what they suggested is that to scale, you really have to store a large amount of data on chain. On chain data should be a lot. In this whole program, what I'm trying to focus mostly are some of the fundamental concepts, and because these concepts will help you to build applications. So once you look into some applications, and in the afternoon I'll talk about when and when not to use blockchain. So these applications will tell you how to use blockchain, and really understand how to use blockchain. these concepts typically help, like, what is a why I'm signing transaction, why I'm hashing a block, why am I why what is the need for consensus, what is the need for reducing storage and everything. So these are really building some basics, though it's a very, there's a courses on blockchain and IoT. I'm teaching much less of IoT, and the reason being that, with all these building blocks and some of the applications that Professor Pal is teaching you, you will be in a very good place to think, okay, fine, given an unknown application, am I going to build it? Yeah. And of course, I mean, the yesterday's session I heard from many of you was very interactive. It really gives you a good feel of how to really implement these applications. Okay, so stateless cryptocurrency is how not to maintain state information, because the state information gets very, very large. Because as we said, that Ethereum stores all the state tribes, right? All the Mughal Patricia tribes. For every block of data, it has a Mughal Patricia tribe, so it is storing a lot of information. So it's about 1.2, 1.3 TBs of data, which is like too much, right? Too much data. So some people, they said, like, we might not be using these might not store all the state information, but we can go stateless. And stateless essentially means how not to maintain the state information. So what I'm trying to say now are some of the proposals that people have said. So current Ethereum does not have these things. But all these, the good thing about this blockchain communities is also very evolving domain. Yeah, it's like people are always trying to make it better, faster, scalable. So that's why secure, and that's why there are many proposals that people have got, and they have their own merits and demerits. So stateless cryptocurrency is essentially promised to not store the state information. So for a client who is storing all the data, it's easier. Then who will store the information? It is with the users themselves. So the main proposal of these stateless cryptocurrencies is that instead of storing all the data on chain, the state data on chain. State data is essentially account data, right? Account information. Everyone will have their own account information only for themselves. And every time it's updating, the account is updating, they have to sync it with themselves. Okay, so it is the onus of the user who has the account. Now, it has good things and bad, some merits and some demerits. The merit is that the nodes which are maintaining the data is reduced quite a bit. On-chain data is reduced quite a bit. However, think of us, like if I have an account, I have to always sync. And I have to show that, okay, fine, my account has been updated. So this is again going to create a lot of bandwidth. So there have been, some real supporters of this stateless thing, and some people who really dislikes, or not dislike, they say that it's not a very good approach. So the thing is that there are different ways in which you can make things better. So the main point that I'm trying to tell you here is that given a design, it's not the only design you can have to achieve that particular purpose. You can do the same thing in multiple ways. And for every way, you have to weigh what is advantage and what is a disadvantage. And later also, this is just not for Ethereum. It's for all systems. I am proposing something. I will have to do a task. What, why, what, how, right? So you have that why you are essentially building this app, for example. What will that app do, and how will you build it? The same thing, whatever support this application is provided, each of you will build it in different ways, right? And for everyone, for each, when each of you build it, you would say like, this is the plus, these are the advantages and disadvantages that you will get, or you will have. So it's just like looking at the same problem in multiple ways and trying to see what works best. Yeah.
Bitcoin is a stateless cryptocurrency, right?
So it's not a stateless thing because they also have the UTXOs, the unspent transactions. So the unspent transactions are kept.
But the data structure is quite small because transactions are like 2,000 and the nodes are 2,000, leaves are 2,000, the height will be quite less.
So with the Bitcoin, okay, so that's a good question. How does, with the UTXO, the thing is that for every user would have the wallet, right? Because they would have their own unspent transactions. So with UTXOs also, that is my state. It's not the account information like this, but it is also my state is in the form of the UTXOs, list of UTXOs that are available in the system.
We said that there are 4 components in each node of Bitcoin. So
what components?
4 components in each block of the Bitcoin blockchain.
Yeah.
So that you said there is a data structure multiple tree in one of them, which shows the hash. So
that's also the transactions.
Of the transaction.
Yeah.
Is there a
Yeah. So there's I did not show it in the picture, but there's a list of unspent transaction, and that also has to be updated after every block is executed.
So all the
yes
currencies that are present in the accounts of all users
yes
that are on Bitcoin.
Yes. So in this case, the state is represented in one way in Bitcoin and all UTXO based models. They don't call it state information, but you have to maintain that UTXOs. Like you can draw an analogy, like this is, in this case, it is the state that you are maintaining. Over there, it's a list of UTXOs that you are maintaining.
Because Bitcoin, the whole blockchain, the data is quite smaller than Ethereum.
Yeah.
That it is, the Ethereum is many TBs, but
yeah.
The Bitcoin one is almost 600.
Yeah, exactly.
Is this the difference between the data structures?
Yes, it's between the data structure. Then there's a lot of pruning and everything that the Bitcoin also does. So so there are many things that you really can do with even with the Ethereum thing, right? And people are essentially, the community is essentially trying very hard to also reduce this storage, because Ethereum also has a proposal for pruning also, and there are many other proposals. But definitely, it's an important component in any blockchain, because all the UTXO based ones like this Bitcoin, Cardano, and Solana, they all have this UTXO based thing. So it works in a little bit different way compared to Ethereum. Okay. Any more questions? So, for example, the last one, when they talk of the stateless blockchain here, they were thinking of UTXO based model actually. So they were not looking into the account based model here. Okay. Okay. So I'm not going over it, but let's talk about. Locker, talk about this, because this is really interesting. So we were asking this question: how much information to keep, where the data is stored. The data is stored, whether it will be stored on the blockchain or with the individual users. So there are many things you can do, but one thing is very important: you have to guarantee a few things, that the transactions on a block are correct. This is very important. So all the transactions that are included in the block are correct, and when you validate the blocks, you actually check whether the transactions are correct. And all the transactions are considered. Liveness, all the transactions are considered. So you remember during consensus, we were saying that all the transactions that a node receives are put in a mempool. Mempool is a memory pool. So essentially, when a node validator node receives the transaction, it puts it in the mempool. So the mempool contains a list of many transactions. And from those transactions, they take a set of transactions in a block. And we were talking like what would be the strategy for including transactions and so on, right? So, there's a big problem. If I have transactions in my mempool, I can ignore a few transactions because, they might be like very, very small value and they might not give me enough transaction fees, right? So I might ignore them because the size of the block is fixed, right? Size of the block is like 4 MB for, I think, Bitcoin, Ethereum also has a limit. So you cannot have too many transactions. So you are picking and choosing from the memory pool. So you could possibly censor transactions. So I might censoring means like I'm not including them in my block. Now this is a dangerous thing, right? Think about it. You have made a transaction and it's sitting out there, it's not getting confirmed. You wouldn't like that, right? So censorship resistance is a really big issue that many of the blockchains don't solve, or they have not have good solutions. And that's why it's very important to have censorship resistance mechanisms. Say for example, incentivizing ways to add incentives in the transactions, or not just the transactions, for the validators as well. Like, I give incentive to the validator saying that if you include everything, I will give you, you will get more transaction fee. So all sorts of things people have been trying to propose to protect against the censorship resistance, but none of the things that we are saying now can guarantee censorship resistance. So I'll pause here.
Queue can be maintained in which only elements which are in front can be talked about.
Yeah.
So why is that key? The validator has to pick randomly the transactions he wants.
Because when we have these blocks, when we have these code running on the validators, they can essentially choose it in any way. They can run their own algorithm to choose.
And at what layer scaling is the best option?
What?
At what layer scaling is the best option?
Layer.
Yeah, on layers of blockchain, like on hardware should we do it?
Oh, okay. Yeah, that's a good question. So, yeah, so whenever you either do it in hardware or in the consensus layer, it is tied with the, it's kind of tied in the sense like, so for example, in the consensus layer, it is tied. You cannot change it. It's not very flexible. Similarly, you can get some speed up if you have hardware, but again, then you would need some specialized hardware. So essentially the blockchain, where is the blockchain? Blockchain is with the, the nodes, the software is running on the nodes. So they have to upgrade their hardware. So not many nodes will be able to participate because they don't have enough, they can't update the hardware. So that's why, there are a lot of proposals to improve the hardware. But sometimes it is not possible because for the mass update, because not all nodes have enough resources to update it. But especially this is very true if you have the proof of stake type of blockchain.
Yeah, actually, if we want to big change like proof of work to proof of stake, then we have to change the hardware. We have to work on hardware only, like Segwit type of things that was proposed on hardware only. So if we want to do a big change,
exactly,
then it's the hardware thing. But if we want to do software like little bit changes, then
a very good point, because these big changes are not very easy. So people don't like to have major changes, right? So all these that we have been talking, the merge, Segwit and all, it took time to be, but Segwit also had a good thing is that, you were you had your previous support, and then you had also the SIGBIT support. So that's one thing. So some transactions can be non-SIGBIT also. So you have a choice. So yeah, I mean, that's the main thing. Like, what is how easy it is for the community to update. Well, tomorrow I'll tell you a very interesting thing where this example becomes very, the thing we are talking about, adaptability, or not adaptability, adoption of a technology. That is quite, it's not a very simple thing. Like, it's not you and me taking decisions, right? And before you take a decision, it's not just the technology that you want. You have to have the money, you have to have the people and everything, right? So any kind of big decisions like this, it's not quite easy. So it's very hard to say at which layer we should be doing it in. The layer 2 becomes easy because it's not, you don't need to really bother about your underlying blockchain.
And ma'am, when we talk about the payment channel network, then it's Bitcoin. We are picking up Bitcoin and we are doing
Yeah.
transactions of Bitcoin.
Yeah.
What about on Ethereum? When we talk about layer 2 of Ethereum, so what kind of transactions will happen between the users?
Yeah, so there's some work on, best would be you have a look into this concept of state channels, which is a generalization of the payment channels.
Yes, ma'am.
So I think that could be something to have a look at. So I'm not discussing it here, but we can take it offline.
Sure.
Yes.
She mentioned that when Ethereum moved from proof of work to proof of stake, and hardware changes were required. But proof of work already required more computing than proof of stake architecture. So the nodes already had very good systems of validating. So proof of stake only reduced their burden of only the node had to do the job at one time. So why hardware changes were required?
No, not hardware changes in that way. I would say, so it's not about the change. If someone was, for this case it was fine. You did not have to upgrade. You didn't have to upgrade. Yes. Okay, so there are some layer 2 solutions which trade between this computation and storage. So the way these work is that you could have off-chain storage, you could have on-chain storage. This table that I'm showing, there are a little bit of terminology disputes within the community. So some people would club something in another part. So what I'll do is that I will leave this to you, but sometime you might see something going from here to here, or there could be different interpretations, because all these products also have many variants. So but largely the data storage, it could be on chain or off chain. On chain means the data is all the time it remains on chain, and there are here the case is that the data is off chain, and there are different types of proof for proving transactions are correct. One of them is a fraud proof, the other one is a validity proofs. So let us talk about both. Everything. I'll just give you a main idea of what a fraud proofs look like and how the validity proof look like. And then I will also talk about optimistic and ZK rollups, because these are getting very prominent nowadays. Okay, so there's something called Plasma. What Plasma does is that this is again layer 2. So it will take multiple transactions. There is an operator. Operator will take all these transactions. Its task is to sequence the transaction. So sometimes the sequencer or operator are separate entities. Sometimes it is together. So what these operators do, they will sequence the transactions and they will club together these transactions and update the state and write to the blockchain. Now, so the operator will bundle a set of transactions, and then these are processed on the plasma chain. So essentially, this is also when I say it's a chain, it's again actually a different chain. Okay. And then the state is written on chain. So the state is updated. So multiple transactions happen. The state is updated, and then you write it on chain. Now, when I say that the state is updated, it means that you can have many transactions all done in layer 2 and update the states on the layer 1, and the validation is done on the layer 1. So the good thing about this is that whenever validation is done on the layer 1, it means that it preserves the security of the original blockchain. So that is a reason why these sort of these sort of things are quite acceptable and easier to deploy.
Operator will not be something like centralized thing, because
That's a good question. So yeah, so this operator and the sequencer. So sometimes the operator and sequencers are same entity, sometimes they are different entity. These should be a decentralized sequencer and a decentralized operator. So now the thing is that these operators are extremely, it's very a lot of computations happen on these operators. Okay, so when layer 2s are built, many of the layer 2s cannot support all these computations. So most of the layer 2s that are operating now, they are actually operating in a centralized mode. Though decentralized sequencer is something that should be available for layer 2. And some people always say that, I'm just pushing the burden from here to here. It's somewhat true. And there's you can actually say that, yeah, there's some load that is being pushed from layer 1 to layer 2. But at this point, most of the layer 2s, for example, Polygon, then Immutable, Stark, what is it? Starknet, all these are, I think, not too sure. Don't quote me on this, but most of them are centralized. But they are trying to go to decentralized. So it's not that it's not yet available, but it's in their roadmap.
So anytime they can go corrupt. This side chain.
What happened?
so then, yeah, this is the contradiction. Like, they are doing peer-to-peer network, they are using on-chain for all.
Look, I mean, the thing, I put it in this way, Rome was not built in a day. So this operators that are now centralized, these will also they will also try to decentralize. They're trying to decentralize it, but that needs a lot of research also. So at this point, those who have built these rollups, most of them are in the centralized. But they will be coming up with the decentralized ones. So yeah, at this point, it's not. Mostly not.
The users that are doing the transactions, they might be also connected to the Ethereum as well. So they are connected to Ethereum as well as they are connected to some different operator. They are giving their transactions to them, and then
So multiple people are sitting and multiple chains are running, right? And so they're taking a transaction and they're taking the transaction fees and just validating the transactions.
So you have to pay to both. And at least now, if you are doing on, say, if you're doing on Polygon, I think you have to pay to Polygon.
But why will anyone go on Polygon if he can go on main chain?
This will be faster.
Faster, and I think fees
will also be less. Question. Okay, so let us see, when I say that it will be operator will generate a compressed proof, what is it like? And now there are two ways in which this can be done. Is it getting very technical? Yeah. Is it getting very technical? Hard to understand? Um,
It's interesting.
I'm
good. One more question, maybe out of context from there.
Another thing is that when I try to put myself in your shoes, honestly, I mean, at your age, I wouldn't possibly be able to comprehend all this. So I'm just thinking what way to do this. So what I'll try to do is that for everything I'll just say what the crux of it, not how. Maybe the how I will remove, but I'll just say the how for those of you who are interested. But I will also say like just keep it with the why. Okay. Yeah, it's yeah. Okay, so and the thing is that at this point of time, even if you don't understand, it's fine. But some of you might be really interested, and maybe you will look up later. That time you will, when you read things up, then you will better understand. So I believe that most of you who have come here you really want to get you have some interest, right? Or so it's just to that yeah. I'll try to keep it balanced. So after everything, I'll say what I'm saying all the time, that what is the why we are doing it. But those of you who are thinking this is overwhelming, you can just keep it to the why. Yeah. Okay. Okay. So these the proofs that we talk about. So essentially, what happens is that an operator who sees these transactions would like to compress this transaction in a way and show that these transactions are correct on chain. So they have to give a proof that it is correctness of these transactions. Now, what optimistic rollup does is that it will take the transactions, compress all the data, generate a proof, generate not a proof, it will just write it on chain, compress data or bundle the transactions and write it on chain. Okay. So then the happy path, no one has to worry about. If the posted data is valid data, then the optimistic rollup will perform extremely well because everything is correct. So the final thing is all correct. So no worries. But the problem comes when some of the data, some of these transaction and the data, they don't match properly. So if there's a problem, then the nodes in layer 1 should identify that it has not been done correctly. Okay. So this is a kind of, I would say, a reactive approach. So reactive means when I make a mistake, when the operator is making a mistake, or it is not sending the correct information, only then the users or on chain will take action. What will they do? They will submit a fraud proof. What does a fraud proof do? So they will say that some transactions are fraudulent. Okay, some transactions are fraudulent. And if they say that some transactions are fraudulent, after that, there's a particular window of time when it should wait. And in this window, the other nodes in layer 1 will check whether it is really a fraudulent transaction or it's not. So you give some time to understand, to figure out whether it's fraudulent or not. So that's a good thing over here. And in order to make sure that no one gives a fraudulent proof, everyone who is generating a fraud proof, they have to deposit some money as a collateral. A collateral essentially means that if I kind of a deposit. So if I am giving malicious for fraud proof, this will be slashed from my account. And I will show you that for everything we will make deposits, because blockchain works in this way. Like you make deposits, do certain tasks. If you don't do it correctly, you get slashed. So it's like having a deposit.
If it is correct, you get some incentive also.
Yes, yes. So if you if it is correct, if your fraud proof is correct, you will definitely get incentive. So that is how the optimistic rollup works. It is reactive. It's reactive means only when there is a mistake or when there is an error, then the fraud proofs are generated. Else everything goes properly. The problem with this approach is that you get a window of 15 days, I think. 15 days. 15 days or hours. I can't remember now. So you get a window of time when the other nodes should say whether the fraud proof is correct or not. So that makes the things a little bit slow. So that's how this optimistic rollups work. So the limitations of the fraud proofs are that the validators can generate fraud proofs, and it's a time-consuming task, and you have to wait to have enough transactions and time to generate the proof. So you have to, first of all, there are two things, like enough. It's also slow because so you have to generate the proof. You have to wait for everyone to say whether the fraud proof is correct or not. Okay.
So what was this one? Can you go to previous?
Which one?
And if the time window is too short.
Okay. So essentially, what you could do is that you could wait for some time, right? And you get enough transactions to happen. So now if you wait for a too short a window, you have very few transactions to verify, and that might not be, and then so you have very few transactions. But if you're because what you are doing is that you need to wait to verify these fraud proofs, and also you need to wait to see if the transactions are correct, right? So the fewer the lesser time you wait, the lesser transaction you have. And so it means that if you have a small time window, you have lesser transactions to check compared to if you have a larger time window, and then you would also have so if you have lesser transactions to wait for, then say, for example, if your time window was only, say, a few seconds, and you are actually looking into only a few transactions and generating the proof or not, instead you are waiting and then you are generating for proof.
Is it a time window of giving a fraud proof, or after fraud proof has been given, it takes time to validate the fraud proof? Okay,
there are two things. First of all, you have a set of transactions which have been, you want bundling together, right? And the time window is to have okay, suppose you have created a fraud proof. Okay, now I think I have to okay, you have a fraud proof. If you don't give enough time, so maybe the others are checking, they don't get enough time to validate. And if it is too large, then if it is too short a time, then you would not have
the time of the time window decided. How it
oh, this is a choice that would come from the roll-up designer. So if you are given a very short window, then not many people might be able to say that whether this is correct or not, because they have to also validate all the transactions and see, right? So suppose you have 1,000 transactions. 1,000 transactions, everyone validates, right? And whether the fraud proof is correct or not, the other should be able to validate and check. So if my window is very short, then 1,000 they can check. But if my window is very large, then they have to check maybe say 15,000. That is again too cumbersome. Any more questions here? Okay. Yeah. So then there are other questions. How would I incentivize clients to generate proofs? How will I decide the time window and so on? Okay. So I will move a little bit fast because I have to still finish this, and I'll talk about the decentralized oracles. So in the ZK rollups, it's a kind of a proactive kind of a proactive approach, meaning that for every set of transactions that the operator rolls up, it will give a proof that I have correctly updated the state, that my state has been updated correctly. So what it says is that this is my updated state and this is my validity proof. Validity proof essentially says that all the transactions are correct and the state update is also correct. So in the previous case, everything was just written down. No proof was given by the operator. In this case, operator generates a proof and it says like, okay, everything is fine. I'm giving you a proof for that. So let us see what a validity proof looks like. Okay, let me just put this a little bit down because I think many of you might not be able to see this. Okay, fine. So let us see. So validity proof for every batch of transactions. So the validity proves the following. What does it prove? It proves that if you have a set SI and a set of transaction, this is my set of transaction, and my new state I is a valid state. Meaning that I have a state SI, I have a set of transaction, and my new state is updated according to my transactions. So you remember those trees that I was showing? One belonged to state SI, another belonged to state SI plus one after the set of transactions were correct. After the set of transactions were performed. Now, this proof essentially says that, yeah, this is a correct state transition after all these transactions have taken place. So this is what the proof says. Now, how the proof looks like? This is, okay, the worker tree is different. That has not been implemented yet. And none of the rollups use worker trees. They use a different sort of a proof, which is called a snark proof. I think what I'll do is, I do have some slides on what is a snark and everything, but I think, I will keep it really high level and tell you what it is without going into the nitty-gritties of it. But those who are interested can go through the slides because it's already there. So what we have to do is that give a proof that that with this set of transactions, TX1 to TXL, the new state has been updated from SI to SI. Old state has been updated from SI to the new state SI plus 1. And there are many the ZK rollups, which the ZK essentially means zero knowledge. Zero knowledge comes from the fact that I have no knowledge of something. I have no knowledge. I mean, I'm generating the proof without knowing what is the content. And then there are many implementations that you can see for these zero knowledge proofs that rollups use. Now, in rollups, there's no concept of zero knowledge. I mean, nothing is private. All informations are revealed. So it is like a misnomer to say zero knowledge. It is just a proof, a short proof that I'm going to tell you. Yeah. So maybe I'll talk a little bit about zero knowledge proofs because, this is something I think, at least one or two of you would be really interested in and maybe have a look at later. Most of the blockchain companies, they are very heavy on this thing. Like, and this, like, zero knowledge is kind of a core to many things. So when you say that I understand zero knowledge, it will be much easier for you to really work in many of the blockchain projects. So it's a really very important crucial component. And it's a concept that is a very old concept. It started with this knowledge complexity of interactive proof systems by Goldwasser, Mikhaili, and Brakov. And what we really want to do is that Alice wants to prove that she has an answer to the, for example. So, say for example, I'm telling you that. So this can be a good example. So you want to go to a pub, and I don't know, I mean, here how things work, but in many cases you have to show you are an adult, so you are over 18 years in order to access to certain things. Say for example, at least in Australia, you have to, even to buy a knife, you have to be, you cannot give it to younger children if you want to buy a knife in the market. Anyways, but for example, especially alcohol, if you be over 18 to buy, so you have to give a proof that you are over 18. What is a proof?
ID.
Right? So you take your ID, say your driver's license, or maybe your Aadhaar card or something, you take it, and your date of birth is over there. They can check what's their date of birth and either give you or deny you access, right? So how much information are you revealing? You're revealing everything. You're revealing your name, your address, your date of birth, and all. What do you want to reveal? You don't need to reveal anything. You just need to prove that you are over 18 years. That's it. But in order to do that, you are giving all that information to that person, right? So it's a lot of information. So essentially, the zero knowledge proof would help you do that, because you will be able to prove that you are over 18 without revealing information. I'm proving in zero knowledge. Zero knowledge means I'll give you no knowledge of all the details. I will only be able to prove that I'm over 18.
Is this like a cryptographic technique?
Yes.
There are many nodes of a graph, or like prime numbers, big prime numbers. You can know the factors, but you don't reveal it. But you show that I know that.
Yeah. It's exactly not like that. But so the proof is essentially a string. Okay. The proof is essentially string, and it is constructed with some mathematical constructions. As much from now, but I can talk to you later how these are constructed and so on. Okay, so this is something that has been there for a very long time. Say for example, Alice wants to say that I know the solution to the Sudoku, but she doesn't want to reveal the solution. So she has to prove that she has been able to solve without revealing it. So the question comes like, how do you prove it? It's something like this. If you give them the solution, gives the solution to Bob can check very quickly that yes, this is a solution, right? You solve a Sudoku, you give the Sudoku solution, then Bob can check very quickly, right? And easily. The challenge over here in zero knowledge is that you are not revealing the solution, but be able to give some proof from which Bob can say that yes, Alice knows the solution. So it's not very intuitive. If I'm talking, it's not very intuitive, right? But So that is why it's a mathematical proof that that is required for all these applications. So when I say the state is changing, what does a proof look like? So I'm just not talking about it at the moment because it's a bit of a involved maths, and I won't be able to discuss that in this time frame. Okay, so so let me just skip over these. Okay, but let me say how this would look like. So so there's a statement. So I'm over 18 years. This is my statement, and I'm giving you as a proof my date of birth. It will generate a proof pi, and the verifier algorithm knows what I'm trying to prove. If you look at the proof, both of us will have the statement. If you look at the proof and say yes or a no. So the prover algorithm takes a statement and then input here the date of birth. It generates a proof, and the verifier is able to verify the proof because it knows what the prover is trying to prove. So this is a zero knowledge proof, and then yeah.
Here the Alice is giving a date of birth. So
no, Alice is not giving a date of birth. Alice is giving this proof.
And this proof does not contain her date
no.
of birth. But she's proving that she's a Babuji.
Yeah. That is why I'm saying this is in zero knowledge. Zero knowledge means the verifier has no knowledge of X. Verifier has no knowledge of X. So there are two properties. I think, these are the things that you will learn in your theory of computation course, many of you. Has anyone done that course? No, not yet. Not yet. Not yet. Okay. Okay, so the completeness, if the statement is true, then an honest verifier will be convinced of this fact by an honest prover. And soundness, it is infeasible to generate a valid proof if the statement is not satisfied. So these are the two properties that this proof pi should have. And apart from that, these are the properties, and extra property is that you want this system to be very efficient, meaning that this proof should be short and the verification algorithm should be very fast. So now let us look how this is applicable to our setting. So you see that the operator is a prover. It is proving a statement, proving that the state has changed from Si to Si plus 1, given a set of transactions. Here, the zero knowledge property is not there, but it is generating a proof. And the verifier is able to verify that proof. So there is a pi, the proof pi. This is a validity proof. The verifier algorithm takes this proof, and it knows a statement that my state should change from Si to Si plus 1, because both the states are written on the chain. And the verifier will return true or false depending upon the proof that it has received and the statement that it already knows. Now, yeah, so these are some of the questions. You can ignore it, but this is how the validity proof works for a ZK rollup. And this is one of the technique to do this. Now, what sort of a proof is this? This is called a snark proof. Forget about this. Maybe we can just skip it. But at the moment, you can just keep in mind that two things. Two things are that the proof should be very short. This proof that I was talking about should be very short, and the algorithm should be very fast in order to verify correctly. So these are the two properties that you should be having.
Aren't we making these proofs transparent also? Means whenever operator is proving, is he putting the proof also on the chain?
Yes. Yes.
So it will be visible to everyone.
Yes. Only because it's visible, it will, the layer ones are able to verify. Yeah.
It's because the probability of finding a solution to that problem is very small. So no one will be able to find a solution, and only the one who proposed the problem knows the solution. That is very transparent, right?
No. So this transparency is a different. This is, you are looking at this word transparent. Don't look at this transparent. Okay. Yeah. There's no transparent. There's no probability here. Probability comes because of this fact. If it is correct, then it will be able to prove. If it is not, with a very high probability, it will say it correct. Okay, forget about this. This is a wholly different thing. To generate such a proof, sometimes you have to rely on some trust assumptions, and the transparent ones do not rely on trust assumptions. So that's why this is a transparent setup. Okay, fine. So, but the main thing to take back here is that whatever validity proof is being generated, it is very short, very small, because you don't want a long proof, then it will be a lot of communication overhead. And then computationally, you have to be validated very quickly. So that's, the validation is very fast. Okay, there's one thing that I've written here. Maybe I'll talk about that a bit, because that is quite an interesting thing. Okay, but any questions before that? Any questions? Okay, this I will really talk about this quick, just to tell you that this is another thing that you should be aware of, especially if you are doing security. If you want to study security, this is something you should be aware of. So have you heard of quantum computers? Have you heard of quantum computing?
Yes.
Yeah. So quantum computers are very interesting computers. They have an interesting model of computing where you're not so for example, the way information is stored in our normal computers is in what? Bits, zeros and ones. In quantum computers, it's like, it works in a very different way. It works with it's a different model, and there it's like a photons, and they have a lot of photons, and the photons can be in multiple states. So these are called qubits. So instead of zeros and ones, they could be in multiple states at the same time. So for us, it's an on and off. For quantum computers, that can be in multiple states. And the the important thing about having quantum computers is that all the computations that you normally do in classical computers, you can speed up in the quantum using quantum computers. So this is the only thing that you can take back from quantum computing. If your computation takes a long time in your normal computer, it can be made faster, can be made more efficient on a quantum computer. Many computations. So because it works in a different way, we don't have to understand what way at this point. But even for really hard problems in computer science, which takes exponential time, these can be solved in polynomial time using quantum computers. Okay, so quantum computers are kind of becoming very hot topics, and because they can speed things up. Now think about it, that this AI, now you're using ChatGPT to generate all these images, right? Everyone is. It is very, very, very computation intensive, right? It's but
Recently on cable images, the GPUs are melting.
right, GPUs are melting. Yes, exactly. So that's the amount of computing you are doing. So with quantum computers, it's expected that it's going to be much, efficient. However, all these quantum computers can bring many, many interesting things. It can do many computations very quick. It's kind of revolutionizing the way of computing and all these good things. That's all good. The only drawback is in security. So I've been talking about cryptography and so on, right? From the very first class. And I told you what a public key what is public key cryptography, right? We saw the digital signatures. We saw, the digital signatures. However, these digital signatures will be broken if you have a powerful enough quantum computer. We are still not there, but there's a big threat coming, for your information.
Excuse me, I had a question. How much quantum technologies they will be enough to crack the hashing techniques or hashing functions still anonymous?
No, nothing anonymous.
No, in the sense the can quantum computers from the answers predict the hashing functions input or hashing functions will
No,
be
they
unaffected.
no, they are not fully affected. You don't have to change hashing algorithms. You have to
Only
change
the
the key sizes.
cryptographic algorithms are.
Those no, hashing is also crypto.
But
It has like crypto properties.
the one has a predicted answer like ECDSA or like
ECDSA and everything. These will be these are the threats. Yeah. So this is a major problem now. Now you might not be aware of it, or some of you might be. So it's what it means. I'll just tell you what it means. What is the threat? How will you be affected if somehow your crypto algorithms are broken? How will you be affected? Say, for example, the banking and things that you are doing. All these protocols require strong cryptographic algorithms there. Now these will all be broken, meaning that someone can steal your credentials,
but
and they can also see if what your transactions look like and everything. Yes.
post quantum cryptography techniques still are they have they come or
Yes, they have come. They have
been
come.
implemented?
They have been implemented. So, for example, Chrome has post quantum support. There's also some of the VPNs which have post quantum support. You can ask. I'm sitting there.
And even this last week only it's OpenSSL.
OpenSSL.
It
Yeah.
was 3.0. Now they
Yes.
have released 3.5. They have included already for quantum cryptography.
Yes. So now there's a lot of upgrade going on at this time. So this is also a very interesting time for us, especially those who are in cryptography, because we are seeing a lot of things happening in this space. So yeah, I mean the snarks and everything would be affected, or the whole blockchain, because it's using ECDS at this time. It is going to be, if that's going to be broken, it means that your entire this blockchain and everything is going to be this whole thing is going to be disrupted.
So,
So-
ma'am, this idea is used in Zcash, right?
This is used in Zcash,
Yes.
but because I'm not talking about Zcash.
Okay.
Yeah. There's a but good point. There's a cryptocurrency where transactions are completely anonymous. Transactions are completely the transacting parties are completely anonymous, and then the transaction values are completely private. That's used in there's a currency called Zcash which has these features. They also use this snark property, but over here, let me just tell you that even forget about the snark and everything. All the blockchains use digital signatures which are non-post quantum, so there is a big threat. So it's a time when there's a lot of questions to answer. How will we what algorithms we will use? How will we move to post quantum, because it's not very easy. All of us use the known protocols. Now you have to incorporate post quantum support in all these protocols. It's very hard. Just letting you know, because this is a big threat. So if you understand post quantum, it's a good time that there's not too many people who understand this thing. So there's a need for people with this sort of skills.
And We can hire.
Okay. So you also have, you also have a, what is it? You can ask Amit for, tell more about their company after this talk. And they are also looking for people. So talk to them if you are wanting, if you're looking for internships and all. Okay. So yeah, let me not talk about this because uh, we will we will have to do something else. In summary, what I would like to mention that these there are a couple of solutions. So stateless cryptocurrencies and rollups. Rollups are really interesting concepts. However, as we saw that most of the sequences and all, they are still not there. They are mostly centralized, and making them decentralized would be a challenge that many of these rollup operators are rollup providers are trying to solve. And there are a lot of these core crypto challenges that should be available, or that we should overcome to make these things happen. So with that, I will stop here, and maybe we'll take a 5 minutes break to come back and talk about the oracles. But the oracles I will teach at a very high level. So yeah, okay, 5 minutes. Come back in 5 minutes.
So my son,
Okay. So, hello everyone.
Hello.
So we'll start with a very interesting thing, which is called a decentralized oracle. Okay, so first question, what is an oracle? Oracle is a database, of course. Software, yes. What is the meaning of the word oracle? Meaning. Many of you have your phones, phones with you. What is oracle? What is an oracle? That is a database. But what is the English meaning of oracle? Oracle is a, they have derived that name from there.
Just prophetic predictions.
So essentially, an oracle is something, you ask them something, they will always be able to answer you. They know all kind of a thing, like they can say.
When you ask God something, he says the right answer.
Yeah. So that's an oracle. So what it means, is that it's so this structure or these oracles, you are using them to get something, get some output. You are giving an input or giving a query, and they will give you a result. Excuse me, can I get your attention, please? So you are making a query, and then you are getting a response. An oracle is giving you a response. That's it. So these we'll talk about the decentralized oracles because they play a very important role in many applications, including IoT applications. So what we have seen is scalability issues in blockchains, different scalable solutions, scaling solutions, roll-ups, and a few challenging challenges. But in this lecture, we will look into applications which are interacting with the outside world. When are we interacting with outside world? In a, say, for an IoT application. What are we doing? How is it interacting with the blockchain?
Storing data.
It's storing data. What data?
Sensor data.
So sensor data, for example. So how is it storing the sensor data? So the sensor is sensing the data. How is it coming to the blockchain?
With the help of a blockchain composite layer.
Yeah, with some kind of a API, you can say, right? What you have to do at this point is that the data that you want to record should be recorded in the blockchain, not something else, right? So there should be a mechanism that can take some external data feed and put it as an input to a blockchain, right? Are you getting the thing, right? You have a application where you have some external data, but you need that external data for some kind of a processing on chain. So there should be a interface that will take that external data and feed it onto the blockchain, or the smart contract that will use that data to do something. So that is the link between the external data and the blockchain. That is that these oracles are really used for, but much more than that. So we are interacting with external inputs. That's something that we are going to see some examples and so on, and we'll define what is an oracle, why we need a decentralized oracle in the first place, some of the functionalities these oracles provide, and some security and privacy properties. Okay, so let us look into applications. You have this IoT, not just IoT application, anything, but for agriculture, for say automotive, for health, you would see many IoT applications available. And what these IoTs will do for agriculture? How is an IoT used?
Soil moisture
Sensor.
Yeah,
Temperature.
sensing temperature, soil moisture, and everything. Then for an automotive industry, how would you use? You have the speedometer. Yeah. Then automatic. Yeah, exactly. Traffic sensing, many things, right? So these are all a lot of devices, sensor devices are there. They are interacting with roadside units, sending them information and so on. They are interacting with one another. The using different small range frequency. Yeah. So yeah, those automotive industries use a lot of these IoT. And then you have health. Where do you use health and IoT?
Pacemaker.
Pacemaker. Then
Surgical sets.
surgical sets. Yeah, okay. Yeah. Then
Smartwatches for using blood pressure and glucose meter.
yeah, smartwatches. Yeah, all these devices. All these devices. Which are tied. We have in our body to
Blood pressure.
blood pressure, and also they are measuring all this information with the several devices that we have around us. So essentially, it is essentially sensing something, right? And as we saw earlier, that blockchains play a crucial role in IoT applications. And could someone say how blockchains are used for maybe these three? I will talk about that separately. Say for agriculture, how you could use blockchain for agriculture.
Sensors,
For irrigation,
For irrigation, but what will you do on blockchain?
all sensors.
Storing like data.
They are light nodes.
Wait. Yeah,
Maintaining,
one after that.
maintaining the irrigations like gap between the consistency of soil.
Consistency, okay.
drip irrigation, for using to transfer water.
So how will you use blockchain then?
Yeah, to maintain the
By
soil cycles of soil.
Uh-huh.
Regular intervals.
For agriculture, product transaction, supply chain, we can use
Some supply chain you can use. Even with the soil, maybe you can, I don't know, maybe, yeah, you want to know like how you're recording something and then
Soil sensors.
soil sampling and things like that. So, yeah, you had something?
The whole the process at what time the crops are planted, the time stamps to be maintained.
Time has to be maintained, everything. That you can use blockchain. Then automotive. Essentially, we will be doing a couple of exercises in the afternoon. One would be like when to use and when not to use blockchain, right? So this is a good, warm up for that. Think during your break. Okay, so there are many, IoT applications which would rely on blockchain, but don't forcefully use blockchain. That's the point. And this finance and all, these are quite interesting applications. These are not IoT, I would say, but these are applications where we will see oracles, where you have external price feed and all that would be necessary to determine, how much loan to provide and so on. So, for example, to really understand, get some idea about a person's history and everything, and to figure out how much loan you can provide to that person, looking into the credit history and all. So these are all use cases where this oracles have been used. Think of a normal transaction, which is a transaction between a buyer and a seller. So seller wants to sell a book, a buyer wants to buy it, right? This is a very simple thing. Would you like to use a blockchain here?
Yeah, transactions, IDs. Like seller needs some IDs. Seller needs some IDs to sell the book.
A lot of books are
For this,
sold
you
in
can
a
store
day.
this transaction and
Collect all
match it.
Okay, one at a time. Who will say? Go ahead.
Yes, no, we can use blockchain.
Why?
Because the transaction made between the two persons, peer to peer, if it is not only one buyer, it is more than one, more than seller.
Not convincing. So, for example,
What was the question?
okay, so all of us, we have to have convincing answers. So, for any application that you want to put a blockchain, you have to say like why you are putting it on blockchain. This is very important. You have something
Regarding the history of
regarding the
transaction history, to store safe and secure.
transaction history.
For example, multiple stores of same company operating in many cities, and they have a single blockchain on how at which time which books are sold in the bookstore. So it can be maintained for transaction data.
Okay, so you can maintain some transaction data by noting down where the books came from or whatever. At what time it was sold, by how it was packed, and all, like maintaining either the supply chain or something, as you mentioned, of the supply chain. So, yeah, so think of this normal transaction, but between a buyer and a seller. Buyer and a seller, think about it that you have bought a parcel, I mean, they are bought something from Amazon, bought this book from Amazon. Amazon does not, give you the book. What will you do?
Collect from stores.
Warehouse.
What?
Customers.
Collect from store.
Customer support.
Customer support.
No.
Customers saying
Collect
the
from some book warehouse.
Like bag it from them.
yeah. No, what I'm trying to say is that suppose listen to the
transaction
question.
meetings.
Yeah. So the question is
Warehouse store.
Yeah.
Amazon seller.
yeah. Wait a minute. Let me tell you the question again. So suppose Amazon does not give you the book, does not deliver you the book. What will you do?
As right questions are.
And basically, you're saying you've given the money, but the book does
Book
not.
doesn't come.
Customer care.
Customer care. Customer care does not reply.
Make them phone.
Go to the police station. Complain.
Call them.
We can maintain a sequence on the blockchain that we have paid, but payment is we have not
Right,
received the book,
cycle.
so that is transparency.
Yeah. So for example, suppose Amazon does not reply back to you, or there's no support that you have been given. What will you do? What will you do?
Cancel the transaction.
Nothing is cancelled. What is your last recourse? You tell me.
File a complaint.
File a complaint. Whom will you file it with?
Consumer.
Sorry, consumer court. So this does not happen. But think about it. Like it's a valuable thing. A book can also be valuable, right? A book can be very valuable. But then the last recourse is to go to the court, right? Because you trust the court. You trust the court to go to the court. And the court is actually arbitrating the whole thing. So if, or it could be other way around. Amazon might say, look, I mean, the customer care might say, no, we have not received your money. And the receipt you generated that's showing me is a false receipt. So many people are generating false receipts, different ways. I'm showing a false receipt.
In that case, we can use smart contracts.
Exactly. I mean, these are some things that you have to really think. When am I going to use blockchain? This is a very important question to ask. So, for example, you both the buyer and seller, they have to go to the court to settle this dispute. Okay, they'll have a dispute. Neither the buyer nor the seller is trying to yield, is willing to yield. So they have to go to the court. That's the last resort. We are assuming that the court is trusted entity because we have trust, we have faith in the our judicial system. So what do you do in the court? What will you do in the court?
Provide the proof.
Huh?
Provide the proof that
Yeah.
it is not delivered and
Yes. So you have to provide proof that that some evidence that the book was not delivered, or I have paid, and then they will ask the seller that where did the book go, and they will give all these evidence. They will do a lot of things in order to prove who is right and who is wrong, right? That's how things work. So instead what can you do with a blockchain? What can you do?
Instead,
So your source of truth or the most trusted entity is your court. Now, what did we say? We have the blockchain in many nodes and they are all behaving honestly. You trust that network. So what will you do? Instead, you would go to the no. Instead, you will go to the blockchain. And blockchain will keep all this information. So essentially, you would say, look, I have given you this evidence. Blockchain will look into that evidence. It will see both the people's evidence, and then who will decide? How can a blockchain decide? No. How can a blockchain decide? They will look into evidence, but then what will they do? You have some evidence. What will they do?
History.
They will look into the history of transaction. Essentially, what is happening there?
Blockchain is just showing the evidence. And
Blockchain is showing some evidence.
And we are just using that evidence to show to the court.
Yeah. Who? We mean who?
We, that is the court, the buyer.
Who makes a decision? Who is right or wrong?
Courts.
Court. There's no court. That's what I'm saying.
Blockchain.
Blockchain. How?
Validate that.
Validating what?
Transaction history of both the people.
So essentially, what will you do? You will run a smart contract that will take as input all your evidences and have some way to decide whether who is right and who is wrong. And how will you decide? Essentially, how does a court decide? It looks into the evidence. It has some rule book to decide, under what conditions who can be right or who can be wrong. So everything is coded in law. And in this case, everything is coded in your contract.
The proof of stake.
No proof of stake here. So at this point, we are just assuming it's just a blockchain. We are not considering any particular type of proof. Essentially, there would be a smart contract who will take all the evidences and figure out and run all these rules that the court was initially running. It will run it. It will codify all the laws. It will run the smart contract on the input, on the evidences, and then say who is right and who is wrong. And then what the only assumption over here is that you are trusting the blockchain, just like you are trusting the court. This is one example why a blockchain could be used. It's for arbitration. I mean, it's a source of truth. You are actually helping to arbitrate this kind of a dispute. But note one thing: what will the seller do in order to get this service? What it will do is that to be accountable, what the seller will do is that both the buyer and the seller both the buyer and the seller, they will deposit some money on the blockchain. Both the buyer and seller, they will deposit some money on the blockchain. This is for the seller. It is okay. They will first negotiate the price. We are just assuming that the book of the price is known and the buyer is willing to pay that money. Let us assume that. So the seller puts a deposit, meaning that if it defaults, then this money is slashed. Okay, the seller does not give the right book, then the money is slashed from the seller's account. It's kind of a deposit, and it's the seller sends the book to the buyer and keeps some evidence that it has sent. Okay. Now, what it could be maybe a receipt or something that it will store on the chain, and later, when the buyer buys the book. Initially, the buyer will pay the money. It is locked in the contract. Did you do this locking money in the contract? Do you understand this concept? Yeah, right? So you can hold the money in a contract. Do you understand this? So in a smart contract, you can lock in money. Okay? Which means that the seller has locked in dollar here and the buyer has locked in the exact price of the book on the contract. And later, once the buyer buys the book, the contract will release the money on some signal that the buyer will provide. It will release the money. So this dollar will come to the seller, and because it has not cheated or anything, it will get back its deposit. So it will get all the money back to the seller. So essentially, the seller gets its own money and buyer's money. Good. And the buyer gets a book. Now, all this is good and it's good. If something goes wrong, what will happen? If the seller
amount will be
deducted. So the contract over here should be written such that both the cases are coded in the contract. Everyone understands this?
Yeah.
So the code should be such that in the good path, what happens, in the bad path, what happens. Everything is there. So it's just like a if-else thing. Like if this receives, and this is what happens. If this does not happen, then this is how to deal with the situation. So the blockchain essentially, for all applications, this blockchain essentially is a kind of just a contract. The blockchain will have a contract, will run a smart contract that will have all these things. Is this clear? Because it's very important that you understand how to use the blockchain. Because in real, when you will be solving, you will be given an unknown problem, right? You will be given a problem which you have to solve for your solve. And then you have to see if you really want a blockchain or not. If you have a blockchain, how will you use that blockchain? And this smart contract, when I'm saying smart contract, who is running the smart contract again? Who is running the smart contract?
It is on the blockchain.
It is on the blockchain. What does it mean? Where is it being executed? Is it my machine or your machine?
It's on the nodes.
All the nodes.
All the
nodes. So that's why it's not just one person giving a verdict. Everyone has the same code that is running, and they're, everyone is running the same code and they are giving the same output. That's how this accountability, you achieve accountability with blockchain. So should I continue?
Yeah. Is it pending?
Yeah, this is just the one I've just started. I mean, I still have a lot of slides. So should I move to the next part?
Can we continue
in
after
the,
lunch?
after lunch?
Yeah, it's your tutorial today.
Yeah.
So you can proceed with this first. Then we'll go to tutorial.
Okay, fine. So then I'll leave you with one thing, because that's the crucial part. Okay. So the thing is that we need a mechanism, because none of this is like, everything is off chain, right? This book is going off chain. The seller is, the receipt is off chain. So there should be a mechanism to input the correct data on chain, right? All the data that you have this at this point is all off chain data. It's like nothing is happening on the chain, right? It's happening between these parties. It's off chain. So this interaction that you want, where you would take the external data and write it on the smart contract, write it on chain, is where you need an interaction with the external world. And this is essentially provided with a Oracle. So Oracle is an interface between the blockchain and the external world. And it will take inputs from the external world, write it on the blockchain, or it will do some computation on, the computation for the blockchain.
So, just like in crypto, when we write proof, we assume that this oracle will always give the right answer. It is the same thing here as well.
So that is the purpose, that this oracle will actually correctly give the external input. Yeah, will do everything correctly. But then the question is, how do I ensure that? How do I have an oracle which can do this? In cryptography, when we write proofs, we just assume there is an oracle, right? Here we have to design this oracle that will take this external data and correctly input the internal data, put it on the chain. But these oracles do more than just query and response. They would essentially be an interface for queries. It would be an interface for even computing. So it's a really very powerful tool, and you will see many connections with what we have been talking with the last 2 days when I talk about the oracles. Okay, so stopping here.
Like context of
So,
Yeah,
yeah, please go ahead.
like in the context of buying and selling such smart contracts blocks the money, and once it is approved, it releases the money. Is it the same function of smart contract in cryptocurrencies? Now, what is the function of smart contracts in cryptocurrencies? What does it do?
All the same.
This
Same thing.
It
Same
locks
thing.
the money.
Locks the money. Yeah, locks the money, runs the script, unlocks.
Once the block is added, it validates, then the smart contract releases the money.
Yeah.
And then what is the 1 hour time delay you said it approves the transaction? Are the smart contracts still approving, or it has approved and then we wait 1 hour to?
Okay. Yeah, so the smart contract approves, right? That's essentially all that information is on the block. It needs a little bit of, you need some, what would I say? Because when so it needs confirmation or more trust in that activity. That's why we are waiting.
The smart contract is already the block, US block.
Yeah.
For
So
every
this entire transaction is written in this. When I'm saying it's written in the smart contract, it is in the form of a transaction that is written actually on the blockchain.
for every transaction that is happening, is there a smart contract?
Yeah. So for example, if the Bitcoin script that I showed you, that is also a contract.
That is a smart contract.
That is a smart contract. But only thing is that when I talk about smart contracts should be Turing complete. So this has a lot more features. A Bitcoin script does not have that. Bitcoin script does not have that, but it is a logic that you are executing.
Bitcoin script is automated.
Everything is automated here. Everything is automated. Only the code you have is very small, and yeah, it's a very small piece of code. Here you can have anything codified.
The transaction we store in the multiple leaves. Is it the smart contracts we are storing with the transactions, each transaction?
Yeah. Okay. Let me take this offline because this we'll have the next class. Amit, do you have a quick question or can we take it offline?
So basically using this decentralized oracles, essentially we are making blockchains accountable here, right? This is what we are trying to achieve using decentralized oracles. I have
Yeah.
like
No, accountability means the buyer and the seller, they are both accountable.
yeah, but how do we prove that is decentralized oracle is helping to that?
Yeah. So the decentralized oracle is essentially helping to take this information and put it on the blockchain. It is just a connection.
Okay, and later anybody can verify. Anybody can.
Later anybody can verify. So the blockchain anyone can verify. But the only thing is that if this data is not correctly input, then everything goes. There's nothing. There's no point.
Right.
Okay. Thank you so much. I'll see you in the afternoon.
Yeah.